Hi, welcome everyone. I am Vivek from University of Utah, presenting on systematic proof for examining evidence-based tabular reasoning. This is a joint work with Riyaz Bhatt, Atiya Ghoshal, Manish Srivastava, Manish Singh, and Vivek Shikumar. Our hypothesis for this work is any evidence-based reasoning system should demonstrate expected predictable behavior in response to control changes to the input. To verify this hypothesis, we did a case study on tabular inference tasks. The main takeaway of our work is systematic targeting probing can highlight the limitations of tabular reasoning models. Such targeting probes are very data efficient and can work with minimal or no supervision. These probing methods highlight several problems in existing tabular reasoning models, such as they use annotation artifact for making prediction. They often utilize incorrect evidence for making predictions, and they also overfit on pre-trained knowledge rather than relying on provided primary evidence. Now, let's dive deeper into our work and get into details. So let me first introduce the task of tabular inference. This was introduced as a part of our ACL 2020 work. The task is where you are given a premise table and a hypothesis statement. For example, you can see in the right there is a dressage table and then there is a hypothesis statement. Both men and women can compete in the contactless sports of dressage. Now the task is to determine whether this hypothesis statement is true, that is entail, false, that is contradict, or undetermined, neutral. Now let's look at the probing task in detail. So the first step is evidence-based reasoning. What is evidence-based reasoning? So as we can see from the example we discussed, both men and women can compete in the contactless sport of dressage. The hypothesis is entailed. But why? Why this hypothesis is entailed? There are two reasons. First, the model need to look at the correct evidence which is there, and then it has to do reasoning, inference, logical inference on that evidence. For example, in this, the model need to know that both men and women basically corresponding to the mixed gender row, whereas contactless correspond to contact row. Now both men and women can basically means mixed gender need to be yes, and contactless mean the row contact should be no. Now existing model does not provide this highlighted evidence and do the required reasoning step. So what we did? We do control probes or control changes in the premise or hypothesis. These are perturbations which we did so that the model prediction either remain or get flipped. For example, one of the change we can do is delete a row from the table. Let's say we delete a relevant row, for example the row corresponding to the contact, and then see if how does the model change. Model prediction change. Ideally the model prediction should become neutral. So this is what is called expected changes to the model, this thing. Now you can see if we remove the key contact, ideally the model should become neutral. Model prediction should become neutral. Now you can see from the diagram, this is very logical and this can be derived from very logic and simple rules which we will discuss later in the slides. Now we have three types of systematic probes which we study. First is annotation artifact. In this we try to answer the question, can a model make inference about a hypothesis without a premise, that is using artifacts. We studied various types of expressions to alter the hypothesis, namely name entity, numerical, temporal, quantification, lexical, negation, syntactic alternation, and subjective. Let's dive into an example of name entity. For others, please refer to the paper. Now, see the example. There is a table about Kathy Holmes, and then there is a hypothesis. Kathy Holmes moved from Ohio to California. The prediction of this is entail. As we can see, Kathy Holmes was born in Ohio and he now resides in California. Now I can take this sentence, apply name entity as well as dependency fast, and got to know moves mean verb. Kathy Holmes is basically entity, title, and Ohio to California is the location. Now one can make a perturbation which change Ohio to South Africa. Now in this case the model prediction should change to contradict. We tried these things on lots of examples and test two kinds of model. one which use only both premise and hypothesis for making the prediction, and one which use only hypothesis, that is hypo only. In this also we tried two types of perturbation settings for the hypothesis, one which the gold label is preserved and the other where the gold label is flipped from entail to contradict or vice versa. Now we observe that for the label preserved examples, the performance doesn't drop drastically. The performance only drop drastically for the hypothesis only models where just hypothesis is used. This indicates that the model is somewhat overfitting on the hypothesis for making the predictions. It's not using the premise properly. Lastly, we also observe that when we have label flip, where we found that the model performance suddenly dropped drastically. This further verify our claims that the model is actually using correlations between hypothesis and the label to make the predictions. The overall finding from our annotation artifact experiment is, yes, models largely rely on spurious correlation between hypothesis and sentence to make predictions. The next we study is inference selection. In this we basically look at, is the model drawing inference based on the right evidence of the premise. So what we did, we basically systematically alter the premise table by simple operation in order to deterministically change the inference label. Then we count invalid label changes which can be deterministically identified. We tried various types of possible operation. Row deletion, in which we tried automatic, where we delete any random row, manual, where we delete a required row which can be a relevant or an irrelevant row. We also did row value update, new row insertion and row perturbation. Now let's dive into example of row deletion and new row insertion. First we delete any random rows. Here you can see, if I remove the row contact, the model prediction should change to neutral, because if you remove any row, and entail can either go to entail or can go to neutral, but it cannot go to contradict. So that is explained in the determinist state automata diagram, which is there in the center of the figure. As you can see, there are many examples, around 325, where entail goes to contradict, and there are also examples where contradict go to entail, 212. These are significant numbers where the model is basically failing on the perturb examples. We also did a relevant row deletion, where we relevantly delete a row which is we know that are relevant. For this we basically crowdsource the data for human relevancy on the test sets. Now here we can do more fine grained changes, because we know now entail cannot go to entail and contradict cannot go to contradict, because if a relevant row is deleted, then the model should definitely change its label to neutral. Now here we see that we have more invalid changes, which is entail to entail and contradict to contradict, which is much more significant in numbers and contribute to majority errors in this. So this really shows that the model is looking at the wrong evidence to get the right answer. We also did a row insertion, where we insert a row which is not contradicting to table and very related to the table. Here most of the model predictions should remain as it is, which is entail remain to entail, contradict remain to contradict. However, neutral can change to both entail and contradict. But we found that here also the model, although less, but do fail at cases. The last proof we did is counterfactual instances, where we basically see how is the model react if the primary evidence of the table is counterfactual in nature. Does the model overfit to the pre-trained knowledge which it has, or does it appropriately change its prediction according to the counterfactual data? Here we basically do is take the premise table and update some rows by counterfactual data, so that the model prediction either retain or change as needed. Let's look at example. So in the dressage table and the same hypothesis, both men and women can compete in the contactless sports of dressage is entail. But now I take the contact row which is relevant, change it to yes, then the prediction should change to contradict. Similarly, if I take the mixed gender row and change it to no, then the model prediction should change to contradict. Now dressage has become a non-mixed gender sport, and earlier the dressage has become a contact sports. Now the finding of this is basically model relies on information from the pre-trained knowledge rather than looking at the primary evidence for making the prediction. The detailed quantitative results and other examples are there in the paper. I encourage everyone to look at that, please. Overall, our main findings are: first, annotation artifacts, where models, we show that models rely on spurious correlation between hypothesis and inference labels to make predictions. We also show that in evidence selection settings, where model look at wrong evidence for making the predictions. Models are not looking at the right evidence. We also check on counterfactual instances, where models relies on information from pre-trained knowledge rather than making their own correct predictions, or they are using the pre-trained knowledge rather than looking at the primary evidence for making the prediction. In addition, we also did an inoculation study where we fine-tune our model on such adversarial settings, each of the probe settings, and see if the model can now become more robust. But we found that the model, although improved performance on the adversarial sets, all these counterfactual, evidence-based and annotation sets, but it started degrading performance on the original alpha 1, alpha 2, alpha 3 sets. That means that the model training, basically fine-tuning, basically have a data distribution shift, and now it's basically more the data distribution shift where it basically have a negative impact on the model performance. So model has now shift to learn artifacts and other patterns from these data rather than like doing in general becoming more robust. So the major takeaway of this is we design systematic probe which can highlight the limitation of tabular reasoning model. Such targeted probes are very data efficient and can be used with minimal or no supervision. Probing with this can highlight many problems in tabular reasoning model, such as the use of annotation artifacts for making prediction with just hypothesis, ignoring the primary evidence, using the incorrect evidence for making the predictions, and also relying on pre-trained knowledge rather than looking at the evidence for making the predictions. I highly encourage to please visit our poster and also check our paper for more details and other interesting experiments. Thank you all for attending.